All right, on this problem we want to determine the clean bed head loss using the Rose equation. So the Rose equation is going to give us the head loss that would be either in feet or in meters. Now we're given this these specifics related to this sand filter. And so we've got a depth that's provided, 24 inches. We got rounded sand, so that's going to have a specific shape factor that's associated with it. It's got a specific gravity that's provided, porosity that's provided, filtration rate in gallons per minute per square foot, and that's the approach velocity V sub A. We have 50-degree water, and we've got a sieve analysis that has been provided. And so again, the sieves, and some of these are not common sieves, so we're going to have to do some interpolation or interpretation between those to determine what fraction of mass is retained in each one of the sieves. And so in this one, we want to determine the head loss in the system for a clean bed head loss and units of feet. So the Rose equation is this form of the equation. This is in the SI units, but the same could be used for the empirical units as well, and units of feet. And so we have on here approach velocity. This would be the depth of the filter, and then we've got our shape factor, gravity, porosity, coefficient of drag, the fraction of that filter material or the mass fraction that's there, and our lowercase d, which is our geometric mean diameter of the particle sizes that are in that system. And we've got coefficient of drag. This is for transitional flow commonly, but you can also have the coefficient of drag CD is equal to 24 divided by Reynolds number if you're in laminar flow, and that might be more relevant for these types of filtration systems. And of course the Reynolds number that's provided here as well. And so this one's got it in terms of kinematic viscosity that's there. But we can also calculate this Reynolds number in terms, so shape factor, density of the material, approach velocity, geometric mean diameter, and dynamic viscosity. So either one of these could work for our approaches. And so we have these particular values that have been determined or provided. What we're trying to do is to set up a spreadsheet or a table that could calculate these. We're going to be looking at the sum of these variables in this calculative system. And so we need to look at, let's just start with our first set of data. And so we're looking at what I've got here in green. So our sieve size that's there and our percent retained. And so this is a sieve size that passes through a 14 sieve and is retained on a 20 sieve. So going from a larger size to a smaller size. So that's, again, a sieve number 14 is the number of openings per linear inch. And we can pull up a table. We can find this online or other resources. I've got something I found online here. And so we've got, let's see, the number 14 sieve is right here. And we have the data, so the standard opening size, mesh size, inches. So yeah, we're going to solve this in empirical units. Well, not empirical, but English units. And then we've got millimeters here as well, and so the different sizes. So our goal is to determine the geometric mean diameter of these parameters. And so if we look at this, so the geometric mean diameter is essentially the square root of the first diameter times the square root of the second diameter in this system. And so for this one, 1.41 millimeters is for the number 14 sieve, and this would be multiplied by 0.841 for the number 20 sieve, and all that to the square root. And we can solve that, and that gives us 1.088 millimeters, and let's convert that to feet. So that'd be 3.57 times 10 to the minus 3 feet. So just to keep all these units consistent in these calculations. Rounded sand, so that's going to provide us rounded sand That's typically got a shape factor of about 0.82, so that's going to go into this equation. Our porosity is provided in the problem statement, 0.45. Our length, which is equal to our depth, would be 24 inches, and that's going to be equal to 2 feet in this one. Approach velocity, V sub A, and so that was given in 2.5 gallons per minute per foot squared, and we can convert that knowing that 1 cubic feet is 7.48 gallons, and so that's going to provide us with 5.57 times 10 to the minus 3 feet per second. All right, so these are going to be all our variables that we're going to put into this specific Rose equation. Now we got to determine Reynolds number. So again, we've got our Reynolds number. So we're going to have to determine the kinematic viscosity of the water. And it looks like in our problem statement, we are given that 50 degrees C water. That's right here. So we've got to find that viscosity. Let's use the kinematic viscosity form of this equation. And so typically we look this up, we might get it 1.3101 centistokes, and then there's typically conversion factors to get it into our units that we would need for this, and this should be about 1.4084 times 10 to the minus 5, and this would be in feet squared per second. Now we can plug that into the Reynolds number equation. So we've got our shape factor 0.82, that's there. We've got our geometric mean diameter we calculated, 3.57 times 10, and that's minus 3 feet. And then this is going to be our approach velocity that we just calculated, 5.57 times 10, that's to the minus 3 feet per second. All this divided by our viscosity, 1.4084 times 10 to the minus 5, and that's in feet squared per second. And this comes out to be about 1.157. And that's, some textbooks will say that's turbulent or laminar flow. Some textbooks are going to say that's transitional flow. I'm going to go ahead and say it's transitional flow just based on what it's saying in our textbook. But different textbooks have different flow rates that are there. Coefficient of drag, I've seen it up to 2,000 for the Reynolds number, where that's that difference between laminar flow and transitional flow. Coefficient of drag then, so we'll use a different form of the equation, 24 divided by Reynolds number plus 3 divided by square root of Reynolds number plus, that would be plus 0.34 in that system. And solve for that. Coefficient of drag is 23.86. And you would do these steps, just make sure you're being consistent with how you apply the Reynolds number. It's probably okay to use it with this form of it and just assume that it's laminar flow. And you're going to set this up in a large table. So a table is going to essentially be able to do these calculations. You might have to have lookups for the different Reynolds number and viscosities, coefficient of drags that might come up. So I've got essentially a solution here that's been set up. And so here we've got our input variables that have been converted to the right units that are here. We've got our sieve analysis that's right here, and setting up the tables, so our high or low value, percent retained, and this total percent right here should sum to be equal to 1. Now again, if you were provided a marble system or marble filters that were all the same size, then this variable on the Reynolds on the Rose equation, so this term F right here, this is going to be that fraction or percent. That way, if you had all uniform sizes, that would just be equal to 100%. Or just 1.0. in your calculations, and that makes it quite easy when you sum these. But otherwise, you're going to put in those actual percentages that are broken down or provided in your percent retained system that's here. So we've got this particle sizes, geometric mean diameter, got the calculations of the Reynolds number, coefficient of drag, and then we're just summing these terms, coefficient of drag times the percent, the F term or the percent of that gradation divided by D, the geometric mean diameter. Sum these for your entire sieve, and then these variables all go into the Rose equation, which I've got right here, and you solve that complete equation with that summation. And for this example, it looks like we're getting a head loss of about 3.3 feet. Now, some of these, you're going to get something about 3 feet. Some of the students I've seen have been about 2.5, 2.8. It really depends on your interpolation that you use for the sieve sizes that perhaps are not available in a standard sieve chart. And so I think that's where the source of error might occur. But it's going to be, about 2 to 3 feet would be your total head loss in that particular system. And that's it. And that's how you calculate the Rose equation, or using the Rose equation for the clean bed head loss in a sand filter.